right videos this time.
All right, let's talk about the exam results and kind of where we are in the class at this point. I'll turn all the lights off so you can take a nap. Make sure. All right, so this graph is very difficult to read. I understand that. It's hard to squeeze all this data on there. The most important things are, there's the ruler in here. See it anywhere? There we go.
So we're getting the portable budget.
Yes. All right, so I have the 3 exams up here. First exam, we had an average of an 80.5, and we're talking about just the people who are here still in the class, all right? So 80.5, standard deviation of 17. Second exam, average dropped to 75.3, standard deviation of 8.7, which was really good. Everyone was clumped together. And then this exam average was 70.8, and that's taking your at-home sketching problems were 25% of the grade, and then the in-class was 75% of the grade. All right? So I averaged those together, or I computed that number, and that's where I got your exam 3 grades. So average was a 70.8. The red bar graph, or scatter graph here, is exam 1. The blue is exam 2, and the green is exam 3. And I've got it basically ordered where the green, notice the green just descends. That means it's sorted so that the highest score on exam 3 was a 95.7, and then it goes down. So we had 3 A's, 2 B's, 5 C's, 4 D's, and 4 F's. So we've got, what, 8, 10 passing, 8 not passing this exam. Make sense? This line right here, this scatter thing, what it does is for each student, like for example, this student right here, they need to get on the final an 18.6 on the final to get a B in the class, right? Not to pass. I didn't put what it took to pass because it would have made this chart spread out even more. So this is what they need for a B. If you add 40 points to that, that's what they need for an A. If you subtract 40 points from it, that's what they need for a C. So basically, this student needs to get a 58.6 on the final to get an A in the class, an 18.6 to get a B, and a negative something to get a C. So they don't even have to show up for the final and they'll pass. So if you take, for example, like this one right here, 105.62, if that's you, then add 40 to that. That's what you need for an A. So that's not possible. A B is not possible because you need 105. But if you subtract 40 from that, that would be what, 65.62? That's what that student would need on the final to pass. Does that make sense? Yeah, yes.
So that's just your passing.
That's what you need to, well, subtract 40 from these numbers, and that's what you need to pass.
Oh.
These numbers are what you need for a B.
In the class.
In the class, overall, on the final. Because we're really down to, we'll have maybe 1 or 2 more quizzes. But other than that, we're just, the only other big grade out there is the final. So what we're looking at is, when I looked at it all, I believe everybody can still pass. But for some students, it's going to take a grade on the final that they haven't been able to achieve the whole semester. So, and it's not a big group, but I mean, obviously I'm concerned about this group that's, if passing is 70 right here, then there's a group that hasn't passed a test yet, so it's going to be difficult to pass the course if you haven't passed a test. But is it possible? Yeah, it's possible. Okay. Hi, Mary. We have a guest presenter today.
It looks good.
Yes, thank you, Mary. All right.
How was that?
Come on in, anywhere you want, really.
So the only thing left is the final?
Well, we're going to have maybe 1 or 2 more quizzes, and then the final. The final's 25%. So,
That's what we have to get on the final.
well, like I said, there's 2 more quizzes. So if you get zeros on those quizzes, that's going to bring your average down. It's going to make this number pop up a little bit. But if you do well on the quizzes, then that's not going to change much. I'll give you a final number, like the week before, the Thursday before the final, I will give you your number. This is what you need on the final for whatever grade it is that you're interested in. All right. Any questions? If you have something specific you want me to sit there and talk about your grade and sit down with you and look over your test or whatever, just get with me after class, okay? Or during my office hours. Or call me. What did you all think of the test? It was really fun? Is that what you just said?
Fair.
Oh, fair. Okay. I thought you said fun. What do we got? Oh, yeah, here we go, Garrett. Derek? Is Derek here? Tristan? Oh, you just didn't see it then. It was here.
Curve sketching stuff.
Oh, the curves? No, it may have got mixed up. See, Margarita? Garrett, I have your other one here. And that's it. So you thought it was fair? Okay. Well, I'll give you an opportunity to go back and take a look at it and, try and work through, try and figure out, if I didn't like circle what you didn't do right, go back and see if you can figure it out yourself. I've already had some students asking me about, will the final replace the lowest grade and all that, and we never established that as a policy, so I don't expect that to happen. But if you come in here and just rock and roll on that final and do like just completely awesome and stuff, then you give yourself some ammunition, to at least discuss your grade with me. We can go back and review tests and just see where you are, but the number one thing for you is to come in and do well on the final, which we'll talk about. We only meet 4 times now.
Is the final going to be comprehensive?
Well, that's what I said. We'll talk about the final, because obviously it's comprehensive in the sense that you need to know all the topics, but it's just, do you need to know every single little detail of everything that you were tested on? We'll get into that. We are going to meet today and then next week, Tuesday, right? And that's it for next week, because Thanksgiving. And then the week after, we only have 2 classes. So we are down officially to our last 4 classes, including today. So, all right, so the end is in sight. Anything else before we proceed? All right. So I wanted you to watch the video for optimization, or antiderivatives if you did that. Now we actually did talk about optimization a little bit. Yeah, do you remember the problem we did with the folded up paper? Yes, we tore off the corners to the sheet of paper and we folded up the edges. We got in groups and we kind of established that the volume of the container that we made depended on where we cut it, right? And initially there was some thought that maybe it didn't matter how we cut the corners out, that maybe we get the same volume no matter what. But it turned out that there was an optimum solution. Yes? And we used the closed interval method to find it. That's the way we did it. Today, we're going to generalize optimization where we're not going to be stuck in looking at problems where we're necessarily on a closed interval. And so we're going to use all the methods that we've learned to try and solve word problems. And in the first problem that you were asked to look at, there was a rectangle that had to have, it was a rectangular pen. So we're looking kind of down on this thing, like top view. And this rectangular pen has to be made with 100 feet of fence. And there are different ways we could do that, right? Different ways we could use 100 feet of fence to make a rectangular pen. And in the video, I went through a couple of different variations of it, where you could have different widths and different lengths and heights. It looked like the square was going to be the best one. If we use a square, we got an area of 625. And anything other than that was going to be lower. But we'd like to use calculus in order to do this. So the basic idea is this. If we can come up with a function that describes what's happening in the real world problem, right? If that function, if we can somehow get our heads around what that function is, then if it's on a closed interval, we can find its highest and lowest points, right? If it's on a closed interval, we can do the global max, global min, and we're in business. But if it's not on a closed interval, we learned how to sketch them. And in the process of sketching them, we were able to find local maxes and local mins. And we can use that to also find where these optimum solutions would be. So now it's just applying what we've already learned. The main goal is going to be to come up with the function. That's the big thing. All right, so I'm going to take you through this first one. We're going to kind of follow a process, and as we do a couple of these, you'll kind of see how the process is somewhat the same for each problem, but unfortunately it's not like a cookie cutter thing we can do for every problem. So we do have to think. All right, so let's take a look at this one. Does everyone understand the problem itself? We've got 100 feet of fence. We're trying to make this thing. We want it to have the most area possible. We're going to put some chickens in there, and we don't want them fighting with each other, right? So we're going to kind of give them as much area as they can get. All right, so what we want, all right, in this problem is what? The maximum area that we can get out of this fence, right? The maximum area. So I'm going to write that down. I want the maximum area possible.
It's almost like rates of change type setup.
Yeah, because when we did the rates of change, we had like the given and then what we want, and it's the same sort of idea. We're thinking through the problem, we're writing down the information we want, we're writing down the information that we're given, and there's going to be some key things we need in here. And just let me work through this one, you'll kind of see the language I'm going to use for this. So we want the maximum area possible, right? The maximum area possible, which means we need an area function. Why do I need an area function? That was related rates. Why is it that I would need a function that would mean, okay, because the graph of it, right, we'll be able to pull the highest and lowest points off of it. And so if I want the maximum area, if I can somehow come up with an area function, I'll be able to find the highest point on that area function, right? The highest point or lowest point, depending on what it is we want. Here it would be highest because we want maximum, right? All right, so if we need an area function, then let's start off by looking at our geometric shape and tell me anything that you can possibly tell me about the area of a general rectangle. Length times width, right? Area is length times width. We could say length times height. We could say width times height. Doesn't matter, right? It's the two sides multiplied together. That's your area. So I'm going to write that down. So far, I know that if I draw a rectangle, so I'm drawing a picture, and remember in the notes, there are a set of steps that I try and get you to follow here. I'm not going to follow them like, hey, let's do number 1, number 2, number 3, because I want the problem to be a little more dynamic where we're just kind of thinking through it as we go. All right, so we're going to draw a rectangle here. Now, what letters do you want me to use here? I can use W, I could do width, height, I could do length, height, length, width, X, Y. Do y'all care?
LW.
LW, okay. I'll use a capital L, capital W. How about that? Length and width. So in a general rectangle, what is the area of this general rectangle? Area is length times width. Okay, so have we come up with an area function? No, it's an area equation, right? This is an equation. It gives you the area, but in order to know the area, you must know two things, the length and the width. When we say we want an area function, what we really want is the area to be a function of a single variable. And the reason we want that is that we could look at it as like f of x. It's a function we could graph. Pardon? That would be a square though, right? We want to be able to let these things be different. We want the length and width to be different. Let's just follow through this first one. The next one, I think I'll let y'all have a little more freedom to do what you want. But is this so far okay? All right? Now, I'm going to put below this, we need capital A to be a function of a single variable. Not two. I don't want area to be in terms of two variables. I want it to be in terms of one. So at this point, we need to bring something else into the game. And what piece of information in this problem have I not even used or addressed or even considered? I have a fixed perimeter, don't I? The amount of fence that I have is 100 feet. So this is, I'm still thinking about this, right? But I'm going to kind of do something on the side here. So leaving that thought. But the perimeter of the rectangle must be 100 feet. Yes?
So you could do 2 times the length times 100 minus 2 times the length.
Yes, I think you said that right. You're saying, well, what is perimeter, right? What is the perimeter of a rectangle? It's 2 lengths plus 2 widths, right? So this perimeter is 2 lengths plus 2 widths. That must be 100. I'm going to take the feet out of there for now.
Right, and then instead of 2 widths, you could define that in terms of 100 minus 2L, so that you could then get the equation in terms of one variable.
Okay, good. So what this is right here is this is some condition we have on how we build this rectangle, right? We can't just go build this however we want, because we only have so much fence, right? So even though this is a relationship we have for area, length is area is length times width, there is some sort of, I don't know, what would you call that? Some sort of constraint, maybe? We're constrained to this, aren't we? We're constrained to this? That's what we call it, actually. We call this the constraint equation. All right? This is the thing that is going to dictate how L and W, what the relationship between them must be. Right? Can't just build this fence, make it 1,000 feet long. We only have 100 feet of fence. So this right here, I'm going to box it, is called the constraint equation. Here's our equation for area. We need it in terms of one variable. We don't have that yet. So we go look at this, say, hey, but wait, we're constrained to this equation. We realize that this is a relationship between L and W, and so we can solve it for either L or W. It's our choice. So would you all like to solve it for R or for, I saw R, there's no R up here, for L or for W? W? Okay? W? All right, so how would you solve this for W?
Divide by 2.
Divide everything by 2 maybe first? That all right with you? And then you said solve for W, so I'm just going to subtract L. There we go. So whatever my width is, or sorry, whatever my length is, my width must be 50 minus that length. Agreed? Now I can take this equation, my constraint equation, come back over to my area equation and substitute in, right? So I'm going to replace what with what here? Replace W with 50 minus L. So I'm going to now continue this piece. I'll do it up here. So now what we have is that the area is L times what you said W was, which was 50 minus L. And that's it, right? Hey, Derek, I think your stuff's up there, your test and your other thing. You see it right there? Now, what was our goal here? To get an area what? Area function, one variable. Do we have it? Yes. That's key. So I'm going to change my notation just a little bit here now. Instead of writing A, I'm going to write A of L. And that's just to stress to you and to everybody who's watching you do this, that you now understand you've created the function, right? You now have a function of a single variable L, as opposed to an equation that connected 3 different variables together. Got it? All right. We want the what of this function? The maximum of this function. So what do you think the next natural question would be? What's the graph look like, right? Yes? Do we actually need the graph?
No, we can figure out what the maximum is. Yeah, just take the first derivative.
First derivative. Okay, so everyone's swinging away at this. This is good. This is good. But there were 2 main ideas, right? Closed interval method versus non-closed interval method, right?
Well, I guess it would be closed because you can't.
You guess it would be. So let's talk about domain, right? That's what we need to talk about next. As soon as you establish the function, consider its domain. Hopefully it's closed interval. Because if it's closed interval, it's pretty simple to get, right? First derivative, set it to 0, figure out where it's undefined, get your critical numbers. Evaluate your function at the endpoints, evaluate your function at the critical numbers, and we're done. Yes?
I was going to say, because it's a constraint equation, wouldn't it have to be a closed interval? I mean, is there any way to go around that?
The fact that we have a constraint equation does not dictate that it's automatically a closed interval. The type of equation we have here will dictate what type of interval we're looking at. The next example that we do is going to be a different type of equation, and you'll see once we get it up here that I don't want to give it away, but we actually have to think about this. Just reason this out a little bit, all right? What is the domain of this function A? So what is the independent variable? L is the independent variable, right? So when I say domain of this, I want you to consider L. And I want you to think about what the smallest and biggest it can be. Or can you even constrain it? Is there a smallest L you can have?
If you take up the constraint equation.
No, you have to stay within the constraint equation. Because you only have 100 feet of fence, right? So what is let's start with smallest. What's the smallest L could be? 0. Do you agree? So it's like, hey, I go tell you to go build this fence. I say, I want the length of it to be 0, and I want the width of it to be... That's a good question. Would it be 100? You got to use all 100 feet of fence.
Yeah, but you have to have some sort of...
You'd have to have 2 sides, right? Your 2 widths, 50 and 50. And then I tell you the space between them is 0. And then I get fired because I'm trying to make you build something that's ridiculous, right? Can't even put a chicken in it. But what we need is something that gives us a lower restriction on L. That will allow us to lock this domain in. So is 0 reasonable for you? It would be a ridiculous fence, but could it be done?
Yeah.
Yes. Now, could it be negative? Well, now you're getting crazy, right? So I think 0 is a good lower bound for our L. So why don't we put 0 and I'm put the brackets because I'm going to say yes, L can be 0. And then what would be the biggest value of L? I think the most common answers I get are 50 and 100. 100 because look, you could make the whole length 100, right? But there's a problem with that. Do you see it right here? What if L was 100? That would force your W to be negative, wouldn't it? And you can't have a negative width. Do y'all see it? So looking at your constraint equation, what would be the maximum you could have for L? For L, 50. But then W would be 0, and again, you'd be building this ridiculous pen that no chickens could sit in. So 50, close it. So do y'all understand these two values are the crazy farmer doing 50 and 0? But somewhere between there, lies the best answer, the optimum answer. So I'm going to use at this point the closed interval method. I'm going to use the closed interval method, right, to find the global maximum and global minimum. So why don't you do that? I already took A and distributed the L through, so why don't you just find your critical numbers for this real quick. It should work pretty easily, right, because it's a polynomial, so derivative is going to be pretty nice. Go ahead and work it out. I'll do it on the board, but I'm going to let you do it on your own piece of paper there. Did you get the books, Mary? Good. So what was my derivative? 50 minus 2L, right? So I'm going to put it here, A prime L, 50 minus 2L, right? And now to find the critical numbers, we set that to 0, and we figure out if it's ever undefined. And I didn't mention this. I'm assuming y'all were all very comfortable with this. We can only use the closed interval method if this was a continuous function on the closed interval. But we don't even talk about that anymore. Why? I mean, why didn't we even talk about it here? It's a polynomial. So, I mean, are you all kind of like past that already? As soon as you see a polynomial, you're not even really considering the fact that the continuity is automatic? Okay. So we've got that. Set it to 0. 50 minus 2L, 0, 25. And then what? This is not something we consider because, again, the derivative is a polynomial. It's well defined. So L is 25. Does that mean our answer is 25? No, we still have to prove that this is going to give us the maximum area, right? We haven't proven that yet. This happens a lot on the final. Give a problem like that. The student sets everything up right. They get this answer, and they just assume that that's your maximum. Now it is. That's the only number it could possibly be. But you still have to show it. All right. How are you going to show that that's going to be where you get your maximum? Plug this L into the original function and plug what into the original function? The two endpoints, which we already know are going to give us something ridiculous. But so now I'm going to compare. I do area at 0, area at 50, area at 25. And so I'm going back to the original function, which is this one, not the derivative, and plug in. When I plug in 0, I get 0. When I plug in 50, I get 0. And then when you plug in 25, you can just compute that on your own, right? 25 in here. Should get 625. I hope it's obvious where the maximum is, right? That's your max. So let's see if we can answer the question, because I don't think we've answered the question. What was it asking? Oh, we did. It said find the maximum area. It could have said find the dimensions of the pen that give the maximum area. So what I'd like for us to do is let's write it all down, okay? I want all this information summarized in an answer here. So we get a maximum area of what? Of 625 what? Square feet or feet squared? Right? If the length of our rectangle is 25 what? Feet. And the width of our rectangle is, okay, so how do we find the width? We go back to our constraint equation, which I've erased, Our width was always 50 minus L, right? So if we plug in 25 here, we can get our width. So we recover that as 25. So hey, you need to build a square, right? And that turns out for anything. If someone gives you a certain amount of fence, they say, hey, build a rectangle that has the most area, then you would build a square.
Why do they specifically want a rectangle?
Pardon?
Why do they specifically want a rectangle?
A square is a rectangle.
Oh, okay.
But not all rectangles are square.
That's right. So you would get away with it, I guess.
Remember that from geometry.
Yeah. I'm curious though, if someone gave you 100 feet of fence and asked you to build an enclosure for chickens, how could you get the most area? Like, obviously if we need to build a rectangle, it would need to be a square. But what about a circle? Would a circle be better?
I guess you could,
Yeah?
like, you could figure out what the circumference would be.
You actually, yeah, we could figure out what that, yes.
It's only if the ground is completely flat though, right?
Okay, yeah. Okay, yeah.
This guy.
So, well, these are good questions because in Cal 3, that's what you try and do. In Cal 3, you're basically going to do in Cal 3, if you do Cal 3, in Cal 3 you're going to do calculus in higher dimensions, so namely three-dimensional space, which is where we live and we like that, right? So it's more applicable to the real world. It gets complicated though. It gets real complicated.
I'm just saying because my plant surveying class, I know there's more area.
Oh yeah. Well, the way it happens in math is, you always have to start with something, a simple formula. And then you keep adding to it. So like there's a formula, if you remember this from college algebra, that all objects on Earth fall at the same rate. So you have this quadratic that models objects falling on Earth, but they tell you like that's if there's no air. You all remember seeing something like that?
Negative 16 squared.
Yeah, negative 16 t squared plus something. Yes, that one right there. That's the one. And the negative 16 comes from, that part is the gravity part. And if you're on a different planet, it's a different number. But anyway, that formula doesn't have air in it. Could we add air into it? Of course, the formula would change. And so what we do is we start with something basic and then we start adding more and more elements to it. And by the time you're trying to solve a real world problem, then you've got to be able to handle the more complicated ones. But you have to start somewhere, right? So right now this is just like this perfect fence that we couldn't even make if we tried to make a perfect rectangle, right? All right, so let's try and kind of summarize what we just did there. Let's just talk through it. We had the word problem, right? We wrote down what we wanted. We determined that there was a function we wanted. We used the geometry to come up with an equation that unfortunately wasn't a function. We used the constraint to then create the function. Once we had the function, what? Domain, right? Figure out what the domain was. It happened to be closed interval. Then that dictated how we proceeded from there to find the max and min. Or in this case max, but it could be min. Got it? All right. Now, unfortunately, not every problem that we're going to see is a farmer building a rectangular fence. So my goal today is to show you some variety of problems. And then next class, because we get 2 classes for this optimization, I'm going to spend 2 classes for this. In the next class, I think we're going to spend more time doing, like, my idea was to kind of do what we've done in the past where I give like each group a different problem and let y'all try and figure them out. But I want you to see some of the variety of the types of things that could come into play. And really there's nothing off the table here. Like trig functions can come in, old formulas from pre-cal, like it's all here, all right? All right, did we talk about this beer can problem? Oh, was it a beer can? It wasn't a beer can. What was it, a can? It was a monster can. Yeah, you still have it. Is that the same one? Okay, so now we're actually going to do this problem.
He brought it just in case.
Just in case. He's been bringing it every day. So we had talked about building this can, right? And we want this can to hold 1 liter, although that's not 1 liter. So we're a company, we're trying to build this can. So it holds 1 liter exactly. And we can build it so it looks like all these different things, right? Do you remember me talking about this?
Yeah.
Okay, oops, I can't get it all on there. So we could have that very ridiculous can that was like a big wafer and that we sip out of that's really short. Or we could have the really tall, narrow can that's like this. You know, we're holding on the floor and drinking out of it like that. Or we could have something in between. And for each of these shapes, there's a different amount of, let's say, aluminum that you would need to cover this or to contain it. And that aluminum costs money, right? So the problem here is saying a can must hold 1 liter, which is equivalent to 1,000 cubic centimeters. Find the dimensions. Okay, this is different than the last problem. The last problem said find the maximum area. This one's saying find the dimensions of the can, or of such a can, with the smallest surface area. All right. And from just the picture here, as I change the radius and this can takes on different shapes, I have the computer calculating its surface area. I know that's hard to read here, but it's obvious, hopefully, that the surface area is going to depend on how we build the can, right? And somewhere in there is the smallest surface area. We got to find it. Oh, hey, you know what I forgot to do on the previous problem? I forgot to graph that parabola. Remember how we found the area function? A of L equals, what was it, 50L minus L squared, right? That was it? I forgot to actually graph this for us. I graphed it on the closed interval 0 to 50. And all we did was went and found that point, that highest point, which corresponded to 25. All right. So I'm going to let you walk me through this one a little more than the last one. Y'all help me out. What's the first thing that I want to do here? So I want, what do I want here? Surface area? I want the minimum surface area of a can. And we're assuming that this can is a right cylindrical can, because you could have cans that are like parallelogrammed over like that, but we're assuming that this is a right circular cylinder. I mean, when you say cylinder, you could be implying something like that, but we're saying a straight right cylinder here. All right, so we want the minimum surface area of a can. Good? Now what? We're going to need to find a function for the surface area, right? So we need a surface area. I'm just going to put SA, is all right? Surface area function. Now what? You have an equation for surface area? None of mine. So let me draw. Remember I drew the rectangle last time and we said L and W and we established what our variables were going to be? I'm going to do the same thing here. I'm going to draw a can. And I'm going to establish my variables. So what do you want to label on this can? Radius. Okay, the radius will go from the center of the can to the outer edge. Call that R, right? Lowercase, uppercase, do you care? Little r. Okay, and height, okay. So the height will go from here down to here. Volume, you have a formula for volume, don't you? Okay, but what are we looking for though? We're looking for a surface area formula, right? Now, we are going to use it, just not yet. Do y'all know what the surface area of a right cylindrical can is? The book doesn't have it, actually. In your formula sheets, it doesn't have it.
Google does.
Google has it. Yeah, so let's think through this, because this is where you can have the difference between memorizing something and understanding something. This can is simply two circles, right? And then this, it's almost like a rectangle that's been wrapped like this in two circles. That's all it is. You agree? Do you know the area of a circle? What's the area of a circle? Pi r squared. So watch this. What I'm going to do is I'm going to take this can right now. I'm going to cut it down the center. Okay? I'm going to can opener around the top and bottom. I'm going to peel it open, and it would look like this, right? Oops. It would look something like that if I did that. If I opened it up. I want the area of all these things together. So this area right here, you just said was pi r squared. This one right here is pi r squared. And now this one's a little harder. Circumference times the height. You know that the distance from here to here is h, right? Because that's this. But when I took it and cut it, right, like this, if you look at it this way, when I open that up, this length is actually the circumference of the circle, isn't it? That length. So what is circumference of a circle? 2 pi r. So I know the distance from here to here is 2 pi r. All right, so let's put these together. The total area, I'm just going to use A instead of SA for surface area. Total area of this thing should be a pi r squared and another pi r squared added together, which is 2 pi r squared, plus the area of this rectangle in here, which is the width times the height. The width is 2 pi r, the height is h, so 2 pi r h. See what I mean when I say the difference between like memorizing something and understanding something? It's, to me, this is more valuable. If you can come up with this formula on your own, that's better than just being like 2 pi r squared plus 2 pi r h is the formula for the surface area of a can. Right? Means you understand what you're doing a little bit. All right, so there's our formula, right? This is our equation. Is it a function of a single variable right now? It is not. To get your area, you must provide two pieces of information, r and h. Then I can tell you your area. I don't want that. I want it to be either just r or just h. With me? So now, what did we do in the last problem when we were at this point? We used some constraint equation to allow us to solve and replace one of those variables in there with something from our constraint. So let's talk constraint. So we need this. Need this to be a function of a single variable. And the only piece of information that we have that's going to help us is the actual restriction here. Look, this can must hold 1 liter, right? That's the big thing that we have not used. So when we say the can must hold 1 liter, volume, right? We know that the volume must be 1 liter. So I'm actually going to write constraint first because I'm thinking ahead. I actually know that this is where my constraint is going to come from. I know that the volume must be 1 liter. I'm going to write 1,000 cubic centimeters because I want to be able to tell you my answer with my length, my radius, and my height in centimeters. All right, that's my constraint. So now you break out your whatever it is, formula sheet, or you think about, again, how do we figure out volume? The volume of a right cylinder like this is just the area on top, right, that circle, times like how deep it is. And how deep is this thing? H. So if that's h and this was pi r squared, then the volume, and you can look this up, is pi r squared h. That's the volume of a right cylindrical can. So that means over here, right in this equation right here, I could say volume, which is pi r squared h, is equal to 1,000. I'm going to drop my units. I'm just going to put 1,000, not going to put cubic centimeters. We'll take care of the units later. And is this good or bad?
Well, we can still solve for one variable.
I can solve for one of these, right? Do you have a preference? H, why not R? If you solve for R, you have to do square root, right? We could, I'm going to try and avoid that. I'm going to try and avoid it by solving for H, which will not require a square root. So divide both sides by pi r squared, and you get H is 1,000 over pi r squared. See what I'm saying about R, though? I mean, it would just be like, just trying to avoid ugliness by having a square root if I solve for R.
You have to really restrict your domain.
Yeah, it might be harder to figure out what the domain is if we do that. Well, let's see. Let's continue. This is our constraint. All right, good. Now what? Yep, you're going to replace this H in this equation with that expression. Yes, there's going to be pi's in there, and yes, and just, hey, we want an answer. We might have to look at something that's ugly. All right, A equals 2 pi r squared plus 2 pi r, and then here comes the h. The h is actually that entire expression. So I'm just going to put times 1,000 over pi r squared. Have I got it to a function of one variable? I do, right? It now just has r in it. A is now a function of r. I can also clean some stuff up, can't I? Got some pi's cancel, that's nice. I've got one factor of r that cancels, which is really nice. And so my area, again, me writing it as a function of r is just stressing to everyone, I realize that I have reached my goal. I wanted it to be a function of a single variable. I have it now. And it's just 2 pi r squared. And then what? Plus 2,000 over r. Now, that's it. That's our function. That's it. It's not a nice polynomial anymore, right? Because of that division by r, it's not a polynomial. Okay, what's next? Once we have our function. Oh, I forgot to name this darn thing. This was the constraint. That function that you get, it does also have a technical name. It's called the objective function. I'm saying this mostly for the people who are going to go on take Cal 3. All right? We have names for these things. This is called the objective function. That's basically the technical name for the function you were trying to look for at the very beginning. You're like, hey, I need a function, right? We call that the objective function. And then over here, we call this the constraint equation. That's helpful later. How many are doing Cal 3? I know it's not a huge population, but okay. You'll hear those words again.
I think I am.
You are. I've decided you're going to take Cal 3. You'll probably take Cal 3 thinking you were supposed to do Cal 2. just like your videos.
He's a probably show up on Cal.
Hey, wasn't this next? All right, so what comes after you have the objective function? What's the next? Domain, right? Domain. All right, and what is it that we're going to look at to figure out domain? Like what? We're looking at R, right? Looking at the R. What's the restriction on R?
Can't be 0.
Can't be 0.
Can't be 0. Why can't it be 0?
Because it be division by 0.
Where are you getting that from?
2,000 over R.
You're just looking at the function.
Oh.
Is that what you, oh, you weren't doing that. I thought you were thinking about the geometry of the problem.
Well, that too.
Okay, so consider them both. You need to look at them both. Think about them both. The function should dictate part of what the domain can be, but also the geometry of the problem itself. What makes sense? Can we throw out negative numbers for R? You're not going to build a can with a negative radius. So we can throw out the negatives. A natural question would be, can you have R be 0? So try and build me a can that holds a liter that has a 0 radius. It's not going to be possible. Or if you look at the function itself, you can't have 0 here, you're going to have division by 0. So 0 at a minimum, but not including 0. This is not going to be a closed interval method, right? We know that now.
To 1,000.
To 1,000?
Or whatever.
Remember, as I build this thing, right, this can, the larger the radius, I start building that wafer, right, that wafer can. How big can that wafer can get?
Very big.
How big?
Extremely big.
Can it be 1,000 centimeters?
Yeah, basically.
Yeah, the 1,000 is only referencing the volume in the problem, right?
Yeah.
Could I build a can that's 3 miles wide in like really infinitesimally thin? Theoretically, could I?
Yes.
Yes, I could.
Probably not wide.
I could let R be as big as I want. All I'd have to do to make it hold to 1 liter is make my height shrink. And shrink and shrink and shrink and shrink.
So to infinity.
So to infinity. Are there any questions on that? That's important, because if you think that this is a closed interval method problem, you're going to run into a major issue. No? All right, so we need to find the smallest, right, point on this graph, the minimum surface area. We want the smallest point on that graph. Now I'm going to go ahead and cheat a little bit. I'm going to show you the picture of the graph first so we know where we're headed. Yes?
Can you, so just for the sake of argument,
Yes.
can you make R be a really big number and show that that would still satisfy the volume of 1,000? Because I'm not really convinced that like you could have infinity, you know what I mean?
You're not convinced that we could have infinite. Well, can we be theoretical though? I mean,
Like, so let's say R, so let's just work it out if like R is 1,000 centimeters.
Okay.
Would that satisfy, you know what I mean?
if R is 1,000 centimeters, then you would put 1,000 right here. Okay, just follow me for a second. You put 1,000 right here. And then what would the height be?
Really small.
Squared, right? So you would cancel one of these. So you'd get 1 over 1,000 pi. So I would need to build a can that's 1,000. Oh, wait, the radius is 1,000. Is that okay? You said 1,000 wide. Radius is 1,000. So I got this can. Its radius is 1,000 centimeters. And then that means the height of this can is going to need to be 1 over 1,000 pi centimeters. And you can give me any number now, and I'm still going to be able to come up with a height that's going to work. Does that make sense?
Take the limit of that.
And you could give me 1 billion. Yeah, you could let R go to infinity. Yeah, okay, think about that now for a second. As R goes to infinity,
It gets smaller and smaller.
H gets smaller. So, but I can keep going, right? So we cannot cap off the end, unfortunately. But let's say we could, okay? It's still not a closed interval because you got a left side that's open. We call that half open or half closed, but we need the closed interval for that method. All right, now there is something subtle here that we need to consider. The closed interval method gives us absolute max and absolute min, right? The other method gave us local max, local min. That never guaranteed us that it was the lowest or highest points, did it? Never did. Let's see what unfolds here. We're going to get lucky, but it's not really luck, it's just the physical characteristics of the problem. There can only be one answer. And amazingly, the way this function looks when you graph it, you can see that there's only one answer. That's the graph. I've got it restricted from 0 to, well, infinity, but if you go and draw this, this is what it does. And we are going to find that lowest point right now. All right?
So just get the derivative.
So we're going to follow the process. Yep. So let's do it. Why don't you take a second to get that derivative? Okay, time's up. I'll put it up here. So I'm going to rewrite some information up here. There's our original function.
So he said 4 pi r.
Oh, 4 pi r, I agree. That's just power rule, right? What about that thing?
But it's not a square.
Oh yeah, it's not a squared. I don't know why I wrote that squared. Thank you. 4 pi r.
You said r to the negative 2. So
Yeah, remember that 2,000 is the same as 2,000 times 1 over r, right? The constant's just going to come for the ride. Derivative of 1 over r is the same as derivative of 1 over x, which is negative 1 over x squared. So this is going to be 2,000 over r squared, but minus. What's that? You could have negative 2,000 r to the negative 2. You could have that, yes. But remember what we're about to do with it. We're about to set it equal to 0, right? Okay. So that's our derivative. And now I'd like to set that derivative equal to 0. And what have I told you about setting derivatives equal to 0? When you have two terms like that, I've always said it's a good idea to do what with it? Get a common denominator, like put them together, right? If you have fraction here, just kind of combine these together real quick. So I'm going to do that up in this step. Can you get me a common denominator on this? So you go r squared top and bottom. 4 pi r cubed over r squared minus 2,000 over r squared. So when we put them together, we'd have that.
So you just said the top.
Yep. And the reason I said to do this is because now to figure out where the derivative is 0, all you do is set the numerator equal to 0. Questions at all? You all seem ready for Thanksgiving and Christmas and no more coming to this class.
No, that we don't like.
Not even ready for this Friday.
All right, we good? Set the numerator to 0. Solve, right? Move the 2,000 to the other side, divide by 4 pi. R cubed is 500 over pi. And finally, cube root. This is the exact answer. R equals the cube root of 500 over pi. That's the exact answer. But I'm going to put this on a number line, right? I'm going to put this on a number line. That would be our step that we do with this. So let's get it as a decimal approximation. So do 500 divided by pi, take the cube root, tell me what you get. I'll tell you if I agree. Anyone yet?
5.019.
5.419, let's go with that. So this is approximately 5.419. We have a critical number. We are not saying that this is a local max or a local min or the highest or lowest point. We're not saying that, right? We're just saying that's a critical number. It might turn out to be the local max, might turn out to be the local min. We don't know. I also need to look at where the derivative is what? Undefined or where it doesn't exist, right? Is that going to happen? Look at your derivative. Does it ever not exist? At 0, right? But 0 is actually not even in the domain of the original function, is it? It's not. But from our experience with, even though this is not a critical number, it's something that we should